This is a review for the first test, which is mostly in chapter 2 and 3. So we began the course with talking about something called displacement. If an object moves from one position to another position, then there's a change in position or displacement, which is the final position minus the initial position. And the time, that change divided by the time is just the average velocity of the object. So displacement can be positive or negative. A positive displacement means it's a displacement to the right, and a negative displacement would be displacement to the left. If you move from one place to another and your velocity is changing, then you are accelerating or decelerating. The average acceleration is defined as the change in velocity divided by the time for that change to occur. Now the change in velocity is in meters per second, and time is in seconds, so the units for acceleration is meters per second or meters per second squared. We can write this definition of acceleration as the acceleration is equal to just v final minus v initial divided by the time. We looked at the special case of constant acceleration. Something moving with constant acceleration, that means it's picking up the same amount of speed every time interval. And we derived 4 equations of motion. The first one is already written on smartboard here in slightly different format. A equals v minus v naught over t can be written as v final equal v initial plus acceleration times time. The change in position is equal to v naught t plus 1/2 at squared, and v final squared equals v initial squared plus 2a times the displacement. And the average velocity, if you are moving at constant acceleration, is just the final velocity plus the initial velocity divided by 2. So, as an example using this equation, let's solve the following problem. A car starts from rest and accelerates at 4 meters per second squared for 10 seconds. How fast is it going after 10 seconds? And then how far does it go after 10 seconds? Well, first thing to do is to write down what is given. So in this case, acceleration is given, time is given, and the initial velocity is given because the car starts from rest. And what are we asked to find? How fast is it going? That's what we want to find, the final velocity. And then later on, we're going to try to find how far does it go at delta x. So we use that first equation to find the velocity after 10 seconds. And the second equation to find how far it went after 10 seconds. So in this first equation, initial velocity plus acceleration, which is 4 meters per second squared, times time, which is 10 seconds, gives us 40 meters per second. That's how fast it's going after 10 seconds. If it's accelerating, you at 4 meters per second per second. How far does it go? Well, it'd be v naught. V naught is 0, so this will be 0 plus 1/2 a, which is 4 meters per second squared, times time, which is 10 seconds squared. So the distance turns out to be 400 meters. (40 meters per second), and forgot to divide by 1/2. It's 200 meters, sorry. 200 meters. What is the velocity as a function of position? In other words, 200 meters. In other words, how fast will it be going at that distance? Well, we can use that equation also, and that will give us actually the same number as we got before already doing it using the first equation. We could have used this equation also. V final squared equals V initial squared plus 2a times delta x, which is 800 meters squared. That's v squared, and take the square root of that, gives you 40 meters per second. So one of the things we looked at was graphs of simple motion, and we saw that if something does not have any acceleration at all, well, it's no acceleration means velocity staying constant. It's not zero necessarily, but it's staying constant. If that's true, then its position versus time graph looks like this. Of course, acceleration is zero, and if the initial velocity was bigger, what would change is that, well, this would be higher and this would be steeper. Now, once we give it an acceleration, then the position versus time is not a straight line anymore, but the velocity versus time graph is in fact a straight line for constant acceleration, and the slope of this line is in fact the acceleration So, looking at the motion of this car here, which graph best describes the motion pictured above? Well, obviously this car is moving at constant speed, which means the graph that best describes it will be the first graph, A. In this case, we see the speed is increasing, and it turns out to be increasing at a constant rate, and so the graph that describes the position will be graph B. Those were position versus time graphs. Now we'll look at some velocity versus time graph. Which of the following position versus time and velocity versus time graphs best represents the motion of an object moving at constant velocity? Constant velocity. So let's look at the top. We need one from the top, one from the bottom. For the velocity to stay constant, this shows you that the velocity is constant. All these other ones, the velocity is changing. It's getting bigger. It's getting bigger here. It's getting smaller here. Now, if the velocity is constant, then the position versus time graph is a straight line. In fact, the slope of this line would be that constant velocity here. So let us look at one of the problems from the web assigned homework. A typical jetliner lands at a speed of 160 miles per hour and decelerates at a rate of 10 miles per hour per second. If the plane travels at a constant speed of 1.6 times 10 to the 2, or 160 miles per hour for 1 second after landing before applying a brake, what is the total displacement of the aircraft between touchdown on the runway and coming to rest? In other words, what is the total distance covered? Now, this is actually two problems. The first problem consists just the first part, where the plane moves at constant speed for 1 second. It turns out that constant speed is 71.5 meters per second. You have to change the speeds here from miles an hour to meters per second in both these places. So, using a conversion factor, those speeds and the acceleration also has to be converted, are 71.5 meters per second, that's 160 miles per hour, and minus 4.47 meters per second squared for the acceleration. And once we have the correct units here, we can use our equations of motion to solve this problem. So, for example, in the very first part, the plane is moving with constant speed for 1 second. So we can use just, there's no acceleration. That means this term in the equation is 0. So the distance covered is just that constant speed times 1 second, the time. And that's 71.5 meters. We can use the time-independent kinematic equation, this one here, to find the displacement while the plane is braking. So the plane goes from an initial speed of 71.5 meters per second here. This is what we got when we converted. When it started braking, it was going 71.5 meters per second, and its acceleration was minus 4.47. So how far did it go? We could use this equation to calculate how far it went. And using that equation, you get 500. Solving that for delta x, you get 572 meters. So the total distance, though, is that 572 plus the 71.5. It's 644 meters. Next, we talked about a special case of constant acceleration, and that is objects that are freely falling, that is moving only under the influence of gravity. And we saw that for those cases, the acceleration due to gravity is a constant for all falling objects, no matter what their mass or weight. And that constant, to be specific, is 9.8 meters per second per second. We're going to just, for a few minutes, round it off to 10. What does that mean, the acceleration of freely falling objects is 9.8? Well, that means that the object picks up speed at a rate of 10 every second. So if it starts off with 0, 1 second later it's going 20, 1 second later it's going 1 second later it's going 10, then 20, then 30, then 40, then 50, etc. And if we use the equations of motion that we just had down there, namely these equations, we can find the distance the object falls. Now, as it falls, in the first second, starting with 0 initial velocity, we're going to use this equation to calculate the distance it falls in that first second. Well, 0 initial velocity means this term is 0, so this will be just 1/2 of 10, which is 5 times 1 squared, 5 meters. That's how far it falls. How far does it fall in the second second? Well, it'll be 1/2 times 10, which is 5 times 2 squared. So it'll be 20 meters, etc., etc. So these two equations are applicable to freely falling objects. If you throw an object up with initial velocity instead of dropping it, well, what that means is that it loses that speed at a rate of 10 every second. So if you throw it up, say, with a speed of 30 meters per second, 1 second later it's going 20 meters per second. 1 second later it's going 10 meters per second. And when it's at the very highest point, briefly, its velocity becomes 0 before the velocity is in the other direction. So now it becomes negative, because down is negative, up is positive. Up is positive, any vector pointing up is positive, any vector pointing down is negative. So the speed here after 4 seconds will be minus 10, after 5 seconds it will be minus 20, after 6 seconds it'll be minus 30. So you threw it up at 30, it came up and down, it landed at minus 30 meters per second. Now, during all this time, the acceleration is, in fact, that number that we call g. Or to be exact, it's minus 9.8 meters per second squared. So a ball tossed vertically upward rises, reaches its highest point, and then falls back to its starting point. During this time, the acceleration of the ball is. Stop the video and see if you can answer the question. And the answer to the question is C. It's always directed downward. The acceleration vector will always point down. That's why it's negative. Negative 9.8. Or sometimes we round it off with 10. At one instant, an object in free fall is moving 50 meters per second. 1 second later, its speed is about. Stop the video and see if you can answer the question. Well, it changes by 10, so it could be 40 or 60. 40 is not here, so the answer has to be 60. If a projectile is fired straight up at a speed of 20 meters per second, the time it takes to reach the top of its path is about. Stop the video and see if you can answer that question. Well, if it's losing a speed at a rate of 10 every second, then it's going to be about 2 seconds in order for the speed to become 0. After 1 second, it's 10 meters per second. After 2 seconds, it'll be 0. Now, we're actually using this equation. We're solving this equation for t, given the fact that the final velocity means the velocity at the top is 0, initial velocity is 20, and this time we're going to use 9.8 here, because that we can't do in our heads as easily as we did with 10. If you solve this equation for t, it becomes 20 divided by 9.8, which is a little bit more than 2 seconds. It's about 2.2 seconds, 2.17 seconds. When a rock is thrown straight upwards and gets to the exact top of its path, which of the following is true? Stop the video and see if you can answer the question. Well, let's see if A is true. Velocity is about 10 meters per second, and its acceleration is about 10 meters per second per second. That's not true because at the very top, exact top, the velocity is 0. So A is not true, B is not true. Velocity is 0 and acceleration is about 10 meters per second per second. Yes, C is true. D also is not true. Velocity is 0 and acceleration is not 0, because if the acceleration was 0, the velocity would remain at 0. In other words, the ball would not come down. So let's work out a problem from the homework, from the textbook and the web-assigned homework that treats freely falling object with non-zero initial velocity. Non-zero initial velocity, in this case, being a ball that's thrown up, not dropped like the other problem we just did, but thrown up with an initial speed of 20 meters per second. And it's thrown from a building that's 50 meters high. So we know that it goes up to some height. At its very highest point, its velocity is 0, and then it starts falling. And we're going to answer a bunch of questions about it. The time needed for the ball to reach its maximum height. And what is that maximum height? We'll start with that. So, we know that at the highest point, the maximum height, the velocity is 0. The initial velocity we know is 20. That's 20 right here. So we're going to use that first equation to calculate the time for the velocity to become 0. So we're going to take v equals minus 9.8 t plus 20 meters per second, set that equal to 0 and solve for t. And then we're going to use the second equation, which is this one here, to find how high did it go during that time that we just found. So we're going to use the second equation here to calculate that. So setting V equal to 0 here, we solve that equation for T, and we get 2.04 seconds. And that's the answer up here. It takes 2.04 seconds. If we now plug that T into this equation here, 2.04 seconds, and solve that for Y, we get 20.4 meters. Okay, so the next problem is find the time for the ball to return to its initial position. Well, you could just double this time. It's 2.04 seconds up, 2.04 seconds down, and you can see that that time is now. You also could have done another way. You could have set y equals 0 in equation 2. If you look at equation 2 in top here, we just used a little while ago, equation 2. When it gets back to where it started from, we're going to call that 0 height, right here. So right here, y is equal to 0. We want to find out when is y equal to 0 if we throw it up at 20 meters per second. So setting y equals to 0 in that equation and solving for t, we get what we got before, 4.08 seconds. So finally, the next question, what's the velocity? Again, you could have just figured that it's going to be minus whatever it had in the beginning, or if you could have used the equation, the second equation up here that we used before, to find the velocity after that many seconds, given that the initial velocity was plus 20. So v is equal to minus 9.8 t plus v naught, so plus 20. And of course for t, we're going to use 4.04 seconds that we found, or 4.08 seconds that we found here. If we plug that in, we get minus 20 meters per second. So the next question is, find the time required for the ball to reach the ground. Well, we can look at the ball that's going from being dropped basically from here, in other words, with initial velocity of 0, and falling this distance, which is equal to 50 plus the distance we found, 20.4, so it's 70.4 meters. How long does it take for this to fall 70.4 meters, starting with 0 initial velocity? And the other way we can do that is that we can just say, starting with a 0 initial velocity up of 20 meters per second, how long is it for y to become minus 50? And this is the way it's done in this example here. We go back to equation 2 up here, and we set y equals to minus 50 in equation 2. So y is equal to v naught t plus 1/2 gt squared, and we set that equal to minus 50, where v naught is being equal to 20, and t is what we're looking for. This is 1/2 gt squared here. So it'll be minus 4.9 t squared. Now, if you do it this way, we have to use the quadratic formula, and we get right off the bat the total time. If we did it the other way, we didn't have to use the quadratic formula. We find the time for it to fall from 0 to this distance, and then we do have to add the previous time to it, the time to get to the top, 2.04 seconds. In physics, we will often need to work with vectors. So let's see how we work with vectors. In this particular case, let's take a look at how we add two vectors. Let's say these are displacement vectors, the red vector and the green vector. And using the tip-to-tail method, we can see that those two displacements add up to the green vector using the tip-to-tail method. But what if you can't find the length of the green vector that easily? So we're going to take a look at another way of doing it, and that is, when working with vectors, it is always going to be convenient to resolve a vector into components. What this means is to take a vector like v here on the right and replace it with components, vx and vy. You can take the vector away. If we know the length of this vector, v, and we know this angle here, theta, we can always calculate the components by using some simple trigonometric equations. For example, the sine of this angle theta is equal to opposite over hypotenuse, so it's vy over v. And solving this for vy, we get vy equals v sine of theta. Similarly, the cosine of the angle theta on that triangle is adjacent over hypotenuse. Solving that for vx, we get vx equals v sine theta. Also, if we know vx, vy, we can find the angle using the tangent, which is opposite over adjacent, or vy divided by vx. And so what this means is that if we have a vector, v, we can actually replace that vector with its components. It turns out that very often it is easier to work with the components than to work with the original vector. As an example, let's say we want to add these two vectors, a and b. Well, if we use the tip-to-tail method, we put this one here, and the green vector, therefore, is the resultant of those two. But let's do it another way. What we're going to do is we're going to resolve each vector into components. Now, in this case, we can just read what the components are. So, for example, the x component of the vector a is just this distance here. And the y component is this distance here. We can read those because we have this graph. And the components of a are these numbers. The x component here is -7. And you can count that off. See it? 1, 2, 3, 4, 5, 6, 7. It's negative. And the y component is 1, 2, 3, 4, 5. We can do the same thing with b. The x component of b is +37, and that means this distance from here to here. And the y component is 7. That's the distance from here to here. So what that means is that we can remove a and b and just leave the component vectors. And those are easy to add. So the x component of the resultant is going to be this minus that. And the y component of the resultant will be this plus that. And if we do that, we find the resultant, the components of the resultant, which is the sum of those two vectors, to be -4 and -12. So basically, we're adding these two numbers to get the x component and these two numbers to get the y component. And you can see this is the components of the resultant. If we put the resultant in here, we can see that this vector has these components, -4 -4 is the x component, and +12 is the y component of the result. So here's the resultant. How do we calculate, in fact, the length of the resultant and what this angle here is? What is this angle? Well, we're going to resolve that. We're going to look at that vector r in terms of its component. This is the x component, and this is the y component. We know what those are. We know that they are -4 and 12. So this is 4, and this is 12. So how do we find what r is? Well, again, using the Pythagorean theorem, 12 squared plus 4 squared will give you r squared. And that's 160, so r is 12.65. 12.65. And what's this angle theta here? Well, theta is going to be the leg opposite divided by the leg adjacent. The tangent of theta will be the leg opposite divided by the leg adjacent, which is 12 divided by 4. Which is 3. So I made a mistake here. 12 divided by this equals 12 divided by 4, which is 3. And the inverse tangent or arctangent of theta will be the arctangent of 3. Now the arctangent of 3 is not 37 degrees like I had here, but it is 72 degrees. So this angle theta right here is 72 degrees. So see if you can do this problem. Stop the tape and see if you can find the components of each of these two vectors here, and then the components of the sum C, which is the sum of those two vectors. And then sketch C in the graph above and calculate its magnitude. Now we can see that using the tip to tail method, what this is going to look like, that this green vector here is going to be the vector C. Now it's going to have negative components. You can see the x component is negative. I'm sorry, the y component will be negative, but the x component will be positive. Let's see if we can calculate those. So the x component of A is this distance here. 1, 2, 3, 4, 5, 6. And it's going to be -6. The y component will be 1, 2, 3, 4, 5, -5. It's this distance. The x component of B is going to be 10. And the y component of B is going to be 3. So the x component of their sum is going to be 10 plus or minus 6, which is 4. And 3 plus or minus 5, which is -2. And so you can see this is -3, I'm sorry. -2, -3, depending on how well you read it. I happen to have read it as 4 minus 3 instead of 4 minus 2. In any case, the resultant, the length of the vector C is going to be 5. And so this is C, what it looks like. It has a y component of 1, 2, 1, 2, 3, 4, an x component of 4, and a y component of minus 3. So here's another problem for you to try by yourself. Stop the tape, and I'll just put down the answers here. The x component of A is this distance, and the y component of A is that distance. So A is minus, that's the length of the red line, minus 6.4 approximately, and that's his x component, and its y component is the blue line here, that's 7.8. Same thing with B. You add the two numbers, and you get the coordinates of the result. A real problem is this example of Huck Finn walking across his raft. He walks across the raft at 1 meter per second, but the raft is traveling down the river 2 meters per second. What is the magnitude of Huck's velocity relative to the river bank? Well, this is what's happening. Basically, what we're doing is we're adding these two vectors. 1 meter per second is his walk this way, and 2 meters per second the river is going. His resultant velocity will be to the right. We will now look at the case of projectile motion. Projectile motion is an object moving in 2 dimensions under the influence of gravity, and its path is a parabola as shown in this picture. Projectile motion can be analyzed by using a vertical and horizontal motion separately. You can see in this picture that the red ball drops straight down, shown this way, and the yellow ball is projected out horizontally, this way. And you notice that they both drop at the same rate, and in fact, as we saw in class, they hit the ground at the same time. In order to approach problems like this, we analyze the motion in the x and the y direction separately. The speed in the x direction is constant. In other words, going left to right, the yellow ball moves over to the right at constant speed. And it drops down simultaneously as if it was dropped down, straight down without actually being thrown out. So basically it looks like the picture like this. The cannonball here is fired, and it drops down. You notice its velocity gets bigger on the way down. Its velocity is always going to be the sum of the vertical and the horizontal components. You see the horizontal component, the velocity on the right stays constant, but the vertical component gets bigger and bigger as if it was dropped straight down. So basically we can analyze the motion by saying in the x direction the object moves with constant velocity. So the distance covered is in the x direction, it's just the speed times the time. In the y direction, however, it drops as if it was dropped straight down. So we use the equation of motion that we've already encountered, that in the y direction, distance equals 1/2 gt squared, and in the y direction, the velocity increases at a rate of g times t. So let's look at an example. This is similar to the example that we did in class. Your teacher stands 5 meters from a wall and fires a dart gun which hits the wall 1 meter below the horizon. So just knowing these two numbers, this distance and that distance, we can answer two questions. How long it takes for the dart to hit the wall, how long was that time, and what was the initial velocity of the dart. To calculate how long it took, we just make believe that we're just dropping an object and it falls straight down. How far does it fall in, sorry, not how far, how long does it take to fall 1 meter for a freely falling body? And we can see that time is given by this equation, 1/2 gt squared. So to calculate how long, it will be 4.9 times t squared equals 1. So this enables you to calculate what t is. Once you know what t is, you use this equation to calculate what the initial velocity is. So this is another example. You may want to stop the video and see if you can do this problem. Now, finally, let us consider the general case of an object thrown up at a velocity at some angle to the horizontal, as shown in this picture. We can see as the object goes up from here to the top, two things happen. You notice the upward velocity, Vy, this is the initial velocity right here, gets smaller and smaller, and it's 0 at the top. Vy equals 0. Vx stays the same. So at the very top, all the velocity is just Vx. And then the downward velocity keeps increasing as if the object was thrown straight up and came back down. So our mission, of course, here is to answer a couple of questions. How high does it go, and how far does it go? So in order to answer that question, let's first calculate how long does it take to get to the highest point. Before we can do that, what we need to do is calculate what the initial components of the velocity are. So this velocity of 100 meters per second at an angle of 37 degrees means the upward velocity, Vy, is 50 meters per second, and Vx is 87.7 meters per second. Now what's going to happen as the object moves, Vx stays the same at 87.7. So it moves to the right horizontally at a speed of 87.7 meters per second every second. The upward speed decreases. Right off the bat, we can see approximately how long it takes to get to the highest point. If it starts off at 50 meters per second, approximately how many seconds to get to the highest point? Well, it's 5 seconds. And if you use 10, if you use 9.8, you can see that it's actually 5.1 seconds. And basically you're using this equation to calculate that. Now how high does it go in 5.1 seconds? Well, this equation tells you how high it goes. We could have also used this equation to find out how high it goes, knowing the initial velocity is 50 and the final velocity at the top of its path is 0. So putting those in here, 50 and 0, we could have used this equation to calculate delta y of 128 meters. So how do we calculate how far it goes? Well, there's two ways to do that. One, if the time for flight to the highest point is 5.1 seconds, then the total time of flight is going to be double that, 10.2 seconds. Now during that time, it is moving to the right at constant speed. So the distance it moves, which is how far away you are, this distance delta x, is equal to its constant velocity times that time we just found. The constant velocity we found is right over here. It's 87.7 meters per second for 10.2 seconds. So this is approximately 900 meters far away. 900 meters far away, right? We can also have found how long it takes to get to hit the ground over here at the end by noting that delta y, as it goes from this point to that point, is 0 because it's at the same height. So setting that equal to 0 and finding solving that equation for t, we also get 10.2 seconds. But let's backtrack a little bit here and go back to the first part of the problem, which states that we are on a cliff 100 meters above the ground. So we're just 100 meters above the ground here. And we already calculated that above this point we rise to a height of 128 meters. So the total height to come from here and back to the ground, the total height is 228 meters. So how long will it take to drop from here to here? We can calculate that time and add it to the time we already found to get to the top of the highest point, which, if you remember, that was 5.1 seconds. So 5.1 seconds to go from here to here, and then how many more seconds to go from here to here? Well, let's calculate that right here. We already had, right, 5.1 seconds to the top, and then the time to fall from 138 meters or 228 meters, right, it is given by this equation right here. Delta y is 228 from top to the bottom. V naught, if you're just looking from here down, V naught is 0. So it's 1/2 gt squared. And solving for that, the time is 6.8 seconds. We're going to add the 5.1 to that. And get a total time of 11.9 seconds. I'd like to point out that we could have solved that equation, answer that question with just one equation by solving this equation right here and letting delta y is the difference in the height from the very initial time it began here, which the height was 0, let's say, to the final time it hit the ground, the height was minus 100. So what we're going to do is going to put in minus 100 for y here, putting in the initial velocity in the y direction, which we know is 87, which is 50 meters per second, and solving that equation. Now, when we set that equation up, it looks like this. It's a quadratic formula equation. In this quadratic formula, we use the quadratic formula right here, putting in all those numbers. We come out, oops, believe it or not, 11.9 seconds, which is exactly what we got using the other way.